load or power source. And we're going to come up to 4 resistors in a row. Out, back, and then one takes a shortcut by everybody. And 1, 2, 3, and 4. And that one's 5. So over here, you can say total 1, 3, 4, 5. Voltage, current, resistance, and power. Oops, I missed that one. Okay, what did I give you? I gave you 24 volts. Am I looking at the right one? Yeah. 24 volts. Is this the one you guys just turned in? No, yeah, that's one you just turned in. So 24 volts. And out here, 120 ohms, 470 ohms, 390, 820, and 1.5K, which will translate into actual ohms. All right, so at this point, we can't solve for anything other than R sub t, right? We in agreement on that, or? So the general rule is combine likes. So any place where I have series, just pure series, I can combine them. And any place that I have just pure parallels, I can combine them. In this particular problem, we've only got 2 cases where we've got series in like. So looks like 1 and 2 can be combined and 3 and 4 can be combined. So 1 and 2, let's see, 20 and 70 is 90 and 1 and 4 is 5. So that would be 590, right? Call that 590. 3 and 4, oh, well, let's see, 400 and 800 would be 1220 minus 10 would be 1210, right? That wheel to go, 1210 ohms. Okay. And then down here, we said this is 1500. So we can't really combine the 590 to anything until we bring the parallels together, right? So 1210 is pretty close to 1500. Such that if it was 1500, you could say the combination of 3, 4, and 5 would be half of 1500 or 750. But since it's a little bit low, I'm going to say maybe 100 low, or it's 300 low. I'm going to say 750 minus about 100. That'd be a wild guess as to what the combination of 3, 4, 5 is.
669.74.
What would you get?
I got 669.74.
So that's fairly close, right? 750 minus 100?
Yeah.
That's fairly close. So you said 669 point something?
7416.
7416. Wow, that's a lot of numbers. Okay. So now we've taken all 3 and 4 and 5, combined it to that. We can now add 590 to that. let's see, 600 and 600 would be 1200, but minus the 10 would be 1259, which would be R sub T, right? 1259.74, how about we call it a 2. Okay, one of the things I noticed a couple of you guys are doing is you're not rounding, you're truncating. So if you look at a number like 0.0419, when you truncate the 9 off rather than rounding it to 0.42, you change the answer by a good 8-9%. That's the point where at that point, particularly as you start multiplying out to power and other values, it's no longer even close to correct. So don't truncate, round. All right. Okay, so now what can I figure out?
Total currents and power.
Well, I can figure out both power and current, but I can also figure out the current for 1 and 2, can't I?
Mm-hmm.
So it's going to be the same value. So now there's another cool trick. You've already got 1259.74 blah, blah, blah in your calculator window, right?
Mm-hmm.
If you have a little button or a feature in your calculator that does something like this, what that does is it flip-flops the two values sitting there. So if I already had this value in and I wanted to divide it into there, I've got it entered backwards, don't I? So I could say 1259, it's already there, divided by 24, flip-flop the two values. Now it's going to divide 24 by this instead. That's a cool feature, right? Okay, so some of you guys probably have that feature in your calculator. It may be a slightly different symbol there, or there may be a second function that gets you there, but that's kind of a handy thing to do. The other thing you can do, many of your calculators will have a memory spot. So if that's a value you're going to use multiple times, store memory. Okay, so either it'll have one memory recall spot, or it might have multiple ones. I strongly suggest you learn how to use those values, particularly with electrical problems. Okay, so what is 24 divided by 1259? Well, it's going to be a really small number.
0.0191.
0.01.
91.
0.0191.
0.0.
0.0191. That's going to be amps. Now I've carried that out to 4 decimal places. I'm probably going to want to do that all the way across. Okay, just to be sort of clear. We said that's the same, total current is the same that's going to go through 1 and 2, so I can plug that in. And that's amps. And that's amps. I can't plug it into here, darn it. I can tell you what the current is going into the branch at node 235, but I can't tell you what's coming out other than the summation of the two would equal 0.0191. That's all I can tell you about that. I also can tell you what the voltage is right here. That's 0. But I can't tell you what the voltage is here unless I establish what the voltage drop is across both of those resistors. Now we know it's probably going to be close to half of the 24 volts because isn't the total value here 669 and 590 pretty close? So approximately half of the voltage will be dropped to here. The other half here, a little bit more, a little bit less, maybe 11 volts and 13 volts, or give or take a little. So 0.0191 times 120.
2.292.
2.292 volts. Now, this is almost 4 times that. So this is going to be basically close to 9, somewhere in there.
8.977.
8.977, okay. So add those up, and I'm going to get 11.2 something something.
69.
11.269. So I can plug that into here, right?
No,
No.
because it has to add up to 11.
Oh, I have to subtract that 11 point something from here, right? Yeah. I tried to pull a fast one on you guys. Some of you were paying attention, some of you were. Okay, so I'm gonna, whatever we said that was. Now, I've already got that value in my calculator. I added the 2 and it's 11 point whatever. Okay, just subtract 24 from it. You'll get a negative number, but you don't care. You know it's
12.73.
okay. Or you could say subtract 24 and hit that button and it'll flip it and make it positive. Okay, so what do we say? It's oh, where am I going to put this value?
5.
Can I put it here in 5? Because the total voltage drop will be felt across 5.
No.
It'll be split across 3 and 4. So we said it was 11 in the low 11, so it's going to be 12 something.
731.
731 volts. Okay. So now, looking at these, I'm going to say that's about 1/3 and that's about 2/3. So the voltage drop here will be about 1/3 of this, or 4-ish, and here it'll be about 8-ish. Right? Interestingly enough, this adds up to 1210, 12.7, so voltage drop is going to be kind of about the same there. But I got a problem. I can't quite calculate it yet, can I? But I can calculate the portion of this that's not going through these two. It is going through here. Okay? So that big number divided by a much bigger number will hopefully give me a number that's smaller than this. If it isn't, I really messed up badly. Probably somewhere down here.
0.0084.
Okay. 0.084 amps. That is smaller than 19.1 milliamps, so I'm okay with that. That seems to be about half of it. Okay, what's 80 and 80, or 84 and 84 is 170. So, what's going to be left over? About 100 and, or got roughly 10 milliamps, maybe 11.
0.0107.
Okay, so it's going to be 0.01
07.
07. Okay, and is that going to be going through both?
Yes.
Okay, again, carried it out to 4 decimal places, some degree of accuracy there. Now, if you guys got fairly good at using those memory spots, you don't even just plug those values in and let them sit in the memory spot. And then while you might write out on your sheet, you might round a little bit and only carry it out to 4. The actual answers you're getting are going to be carried out to whatever your calculator will do. The other thing that's interesting is a lot of times your calculator will carry out further than it displays. Okay, so most of the time that's not gonna matter. The only time it's gonna matter is if you're in a very sensitive digital circuit where really, really low values matter. Most of what we're doing isn't gonna be too bad. So, but just to do a cross check, 820 times times 10 milliamps, 10.7 milliamps. If it was 10, wouldn't we just go dump like that? It'd be 8.2. That's going to be something a little bit less than that. I mean, a little bit more than that. But what's 820 times 0.0?
8.774.
So 8.774. Okay, so a little bit more volts. And then same value times 390 might make it all the way to 4. That's going to be just a little less than 4 if this math works out right. 399.
It's 4.173.
399. What is it?
4.173.
Oh, it actually did. 4.173. When I add all that up, it looks like it's going to exceed my value here, just a hair. Truncating, rounding error. Something happened there a little bit. Okay. Again, I'm not going to worry about that too much. So now all I need to do is the math downwards. Math down, add all those up, and make sure it's the same as the math down here. That's your cross check. If the two values end up the same, you know you did it right. Okay, everybody's golden on that. Okay, so for next week's homework, I changed the rules a little bit. I'm going to give you power and the voltage drop across one of the loads. But there is enough there to sort it all out. Take a short break. Well, we're the other three went.
That's a series right this one.
Took off running.
You don't have any resistances you have to get.
So for those of you that struggle a little bit on the test, I don't think anybody's mathematically out of the running, so don't just run away. If you do reasonably well, if you get a 60, all you gotta do is get an 80 on the next test. You're still in the game. And if you get the 80 on the final, you're well into the game, because it counts for more. Okay. Same thing, if you're doing well on these, that's going to bump you up some. If you're not turning them in, not much I can do for you. Okay. All right, so let's take a short break. I'll get the cabinets open. Presuming Mark is here. Yeah.